Reservations in two-way slabs, case 8. We are in the situation where the slab is simply supported at three sides, and on one side it is fixed. The orange one lines means it is simply supported, and the green lines means the slab is continuous or it's fixed in a beam or a wall. So we will look at cases 6 to 10, and in this video we'll look at case 8. And case 8 is about a type of edge square hole. So it's a square hole on the top where the fixed side is situated. Now let's look into that into detail. We got a two-way slab, and we are looking at the ultimate limit load or the ultimate load by means of yield lines. So we draw the yield lines. We use the simplified 60-30 rule because this is fixed and this is simply supported. We draw the line. This is the same 60 degrees, 30 degrees, on the bottom 45, 45 degrees, and then we make the connection with the yield line. Of course, there's also a yield line at the fixed end. We assume that the plastic bending moment in the field is the same as the plastic bending moment on top of the slide. So top of the slab. So it means in fact that the upper and lower reinforcement are equal. Then we make a reservation, where the reservation is, of course, the yield line is not existing anymore, and it's a square reservation on the edge of the slab, and is situated at a distance d4 from the left-hand side. The conditions for case H is then two-way slab B must be between A and 2 times A. Square hole, of course, D1 is equal to D2. And at the edge, that means the top edge D3 is 0. And we will consider only this time a hole between those two yield lines. So the yield lines will not be cut. It will be between those two yield lines. That means that D4, there's a limitation on it. It must be bigger, of course, for not cutting this line, as S1 divided by S4, because this gives you the tangents of this corner. And D4 must be smaller in such a way that it's not cutting this yield line, so it must fulfill this condition. Now let's look at those different conditions. You can put in, this is logical, but you can put in here some numbers. So then you see that D4 must be between this value and this value. And of course, D1 is always smaller than S4, which means that D1 is smaller than 0.634 times A. By using this rule, you see we have a certain reservation in the hole on the left-hand side, not cutting the yield line, and it goes further on up till to the end. So that's a type of case 8 reservations in slabs. Now let's calculate it. We look at the different areas made up by triangles and the areas made up by rectangulars. We calculate the work done by the external loads, and we use EX, which means E divided by Q delta. Then we look at the rectangular portions, which is the orange ones. So then you have this dimension is B minus 2 times S1, both sides, it's S1, times, of course, A. And we subtract this part where the reservation is, so that's what, minus surface, but the unity of deflection is here 1, or delta, let's put it delta, then at this point, the deflection is delta times d1 over S4, just d1 divided by S4. And then the mean deflection is half of it, delta divided by 2. Then we look at the triangles. Then we will see, of course, we have two sides, A times S1, and there's also A times S1, all compromising all they exist all at summation of triangles. So it's a total surface divided by 3 or by delta over 3, which is the mean deflection. We can substitute the variables, and then we have this formula of the work done by the external loads. We look at the work done by the internal action or the bending moment, and we do that by taking this yield line, project it to this rotation axis. So it's B minus D1, of course, because this is not existing. So it's B minus D1. And then project it over the angle, which is delta divided by the longest distance, which is S4. So that's this term. Then we take this yield line. It's B, length is B, divided by S4. And then the two others, it's A projected on this axis. So multiply by delta over S1. On the other side, we have the same, A divided by S1. And then the one which is left over is this one projected to this rotation axis. So it's B divided by delta over, this is the maximum distance, S2. Then we can put in the different numbers, and we have an expression of the virtual load done by the internal forces. By making E equal to D, we can calculate M, which gives you this type of formula. Notice that on this formula, D4 is not there. It's only dependent of D1, A, and B. So maybe we made a mistake, because this is strange. Because this does not play any role in the maximum bending moment. When you look at it more closely, then you will see that because this reservation is not cutting any yield lines, except this small portion here, but for the rest, it's not cutting those yield lines. So it's a little bit logic that the maximum bending moment is independent of D4. But D4 gives you a limitation on the use of those formulas. You will see that by checking the position D4, you can arrive with this formula at a number which is not applicable. So yes, the formula is independent of D4, but not the conditions. Let's give you an example. Let's suppose we have a square slab fixed at one side and simply support at the others, and we have a reservation of at a distance of 2 meters of 1 by 1 meter. Of course, the yield line is interrupted at the level of the reservation. The depth of the slab is 200 millimeters, the concrete cover 25, the floor finish is 2 kilonewton per square meter, and a mobile load is 10 kilonewton per square meter. Now, what is the reinforcement needed in this slab? We calculate the load in ultimate limit state, which is, of course, 1.35 times the permanent loads plus 1.5 times the mobile load, and it gives you 24.45 kilonewton per square meter. Then we, with those parameters, we use the formula that we've stated on the previous slide, the maximum bending moment. We calculate it and we find 20.59 kilonewton meter per meter. Then we calculate the lever arm in x direction, which is the total height minus the concrete cover minus the point of gravity. And here we start with a diameter 12. If this is not okay, then we go to a higher diameter which is much bigger, or one which is lower. But we choose here 12 millimeters. Gives you a lever arm of 164. The lever arm in the y direction gives you 152 millimeters. And the mean lever arm is 158 millimeters. Later on, we will see what will happen if we do not use the lever arm. So when, for instance, the reinforcement in X direction is different from that in the Y direction, or when M is different from M accent. So when the plastic bending moment on the bottom of the slab is different than the slab bending moment on the top of the slab. So we will see later on how we can handle this. But for the moment, we calculate it with the mean lever arm. So the needed reinforcement is then the bending moment divided by the lever arm and the yield strength of the steel. And we augment it by 10% because this is an upper bound method. We put in the different numbers and we need 366 square millimeter per meter, or diameter 12, 3 per meter, or every 300 millimeters and diameter 12, which gives you 377. Now, this is not very wise because the slab is only 200 millimeters and the distance between the reinforcement is 300 millimeters. It's still okay, but maybe we prefer a smaller gap between the reinforcement. So we can use diameter 10, then we adapt the lever arm, we recalculate it, and you have 362. So a diameter 10 every 200 meters is fine. So preferably we take 5 diameters 10 per meter instead of the diameter 12 every 300 millimeters. Second example, we have a rectangular slab with those dimensions, and it's an existing slab. And the existing slab, we only know that it's reinforced in 2 directions, and top and bottom is the same as reinforcement. But we don't know what was the original load. We don't know what is the exact reinforcement that was put in. So now the question is it okay to make a reservation at the largest edge of the slab? A reservation 1.6 times 1.6 at a distance of 1.7 from the side. So how can we tackle this? Well, because we do not know the total load, we divide the bending moment by the total load. So M0 is the maximum bending moment or plastic bending moment where it was originally designed for. And this it's bending moment without the reservation in it. And you see, of course, that this is only a function of the geometrical parameters. So that's handy because now we can calculate M0 divided by Q, and it's 1.21. We can calculate now the maximum bending moment with the hole in it. Again, we divide the bending moment by the total load. This is a factor only this factor only depends on the geometrical characterizations, and we have 1.21. You see that the bearing capacity is the same, so the reservation there can be made without losing any bearing capacity. So that's good to know. Even we do not know what the reinforcement is or what the original load is, we can make a reservation like that in the slab. Then we look at the definition of the bearing capacity is of course the maximum bending moment without the hole divided by the maximum bending moment with the hole. Or is equal to 100 times the maximum load with the hole divided by the maximum load without the hole. So the bearing capacity is a function of A, B, and D1. For type 8 holes, edge square holes, we must we must fulfill those 2 conditions. That one, that's easy. This is also very easy, but this is the position of the reservation. Remember, alpha 4 is not in our formulas, but we still have to check it. Otherwise, the formulas are not valid. Then we can, with those dimensionless units, we can rewrite the bearing capacity of the slab, and you arrive at this formula. We can put it in a graph, and you see on the x-axis the alpha 1, which is the size of the reservation. On the y-axis, it's the bearing capacity in red for a slab which is a square slab because A equals B. The blue one is a rectangular slab where B is 1.5 A, and the black curve is a rectangular slab where the dimension B is 2 times A. So these are the three extreme values that you can have. All the others are in between. Now let's see what does it give when we have a hole, for instance, with 0.3 as A as a dimension, and we look at the different positions that this reservation can have. Then you see that the formula is independent of the 4, and the bearing capacity is 100%. So there's no loss of any bearing capacity. This looks strange, but this is because there are no we are not cutting the yield lines, and the influence of cutting the yield lines on top is too small to be significant. Now, this condition on alpha 4, it's as follows. That was the condition, and just rewrite it here. And then, for instance, for the red curve, which is for a square slab, alpha is 1, you see that this value here is the bearing capacity at that point. So it's the bearing capacity at point 464 times A. And that's this value is the value limited by this formula. So if you, when you are put in this alpha is equal to 1, then you will arrive at this alpha 1. So this dotted curve gives you the limit made by alpha 4. So this portion of the curve is not valid. It's only that portion of the curve. So we can now do the same with the light blue one, or the blue one. That's for a slab with dimensions 1.5, B divided by A. Again, we fill in 1.5 in this constriction, and we find alpha 1 is 0.696. So this is 0.696, but it's outside the graph. It's here outside. But where those two lines will connect, then it will be at this position. And then we can do the same for the black curve, but this is not put on the graph because it's far away. So it's something like that, and then it's far away. But it's the same reasoning. There is a moment where you cannot use the formulas anymore. What's also interesting is that when you make a hole from type of case 8 or type 8 into the slab, then you will see that until, for instance, a slab dimension of 0.25, which means 1/4 of the size of the smallest size of the slab, there is no influence at all on the bearing capacity. Once you exceed 0.25 from alpha 1, then you will have an increase, in fact, in the bearing capacity of the slab, because you take more load away than that you weaken the slab. A square hole at the edge of a rectangular concrete slab, type 7, has no loss of bearing capacity as long as the yield lines are not crossed.